Yeah, thank you very much for this excellent conference, for the invitation. So it's the end of the day, so probably part of you is tired. I would like to introduce you to this theory. Yes, I have 61 slides, but it will be like a cinema, you will see. So I will begin with a large introduction. So for example, this is one slide. So it happens that the best language which is useful for me is the Berkovich language, so part of the slides will be about that. Then I will little by little show you some features of these differential equations. And then I'm focusing on two theorems on which I had the pleasure of giving my own contribution. So decomposition theorem, so it means factorization of operators. We have seen, for example, last week that this was really important. For example, when you want to prove a theorem like Turretin theorem, so the fact, or when you want to compute a Galois group, it's important to factorize your operator. And then I will tell you something about the de Rank homology of those equations. So this is a very introductory talk. We are using p-adic numbers. And why is this interesting? Well, from my point of view, because some phenomena which are typically complicated over the real or complex number become rather easy over Q. And the converse is also true. Some easy phenomena over the real numbers become probably more complicated over QP, such as the topology, for instance. So here is a short list of things that are typically complicated, but that becomes quite easy over the p-adic numbers. For example, the convergence of a series of numbers. So the series converges if and only if the general term goes to 0. So this is, of course, an excellent thing. And then we have a similar phenomena for power series. I want to know if my series converge. I only have to test if the general term goes to 0. What about, so another nice fact is that if you give me a non-singular point and a solution of a differential equation, then the radius of convergence is never 0. For example, another algebraic phenomena which is very convenient is that the Galois groups are always solvable because we have the ramification filtration. Well, here is a list of things that goes worse. The topology, for example. So I said that the solution converge, but in reality they do not converge enough, let me say, and they present a wide complex behavior. We will see in this talk later on what I mean by this. Then also factorization of linear differential operator has a different flavor, but I will be able to connect this flavor to what you know. And now about the de Rank homology, if you are over the complex numbers and actually the abstraction, so, and you consider the analytic homology, these groups are always finite dimensional unless your domain is really complicated. So the only abstraction to the finite dimensionality is the complexity of your domain, the number of holes that you have. And in particular, the index of the dimension of those spaces, it's kind of independent on the equation. It really depends on the domain. For example, if you have an irregular differential equation by a transcendental base change, such as an exponential, you can transform it into a regular one. Over the p-adic number, There are analytic curves which are really simple, such as open disks. And we have, let me say, the majority of linear differential equations have infinite dimensional de Rank homology. And my goal today will be actually to give you criteria to have finite dimensional homology and a theorem to factorize your operators. Okay, let me provide some setting. I'm considering a field with an absolute value satisfying this ultrametric rule. I want my field to be complete, and I will assume, maybe sometime without telling you, that my field has very good properties, such as being algebraically closed, spherically complete. But I want to maintain the discussion general because I'm interested in the trivially valued case. Please notice that every field can be endowed with the trivial absolute value, and it is complete. So I can do all the Berkovich geometry over it. So let me begin with a couple of simple, very simple but meaningful examples. So this is probably the smallest, the simplest differential equation. So the solution at one point is given by the exponential, and you can, with a little effort actually, or maybe an effort, compute the radius of convergence of this power series. This is required to be able to give the valuation of the exponentials numbers. So if you are in the case of the trivial valuation, every factorial here has valuation equal to 1, and the radius is 1, and it is independent on the point. In p-adic, the situation is similar, but the number is this number. Okay, so you can observe that this function is independent on your point, constant function. Oh, and one question that I can ask to you, because I cannot answer, is why is this radius finite? The exponential is supposed to have infinite radius, right? And if you work over the complex numbers, typically the radius of a solution is just the distance from the closest singularity. So there's a singular point, and then, so you may imagine that the singularities are the obstruction, the physical obstruction to the convergence of the solutions. But here, our equation has no singularity. It's this y prime equal to 1. Where is the obstruction? So there's no obstruction in appearance, at least, and this is a deep question for which I don't have any answer. So in any case, from the beginning of this theory, maybe starting with Dwork and Roba, they have observed that these radii of convergence contain information about your differential equation, and you will see in a moment. With another example for this, I'm trying to write down a very simple example. But as you can imagine, the computation may be horrible even with small numbers. For example, in this case, you find the radius to be equal to this omega, the number we had before, the square root of it, if the value of x is less than this, or this other number if the values of x0 is greater than this number. So here we have another new phenomena, no singularities, but now the radii are not constant. It depends on the point. Well, in this specific example, it depends on the point, on the valuation of the point, right? Only on the absolute value of your point, so the distance from 0, let me say. Well, I can observe also another very nice phenomena. this differential equation has an irregularity which is equal to 2 at plus infinity. And then when the norm of x is becoming larger and larger, this radius has a slope, let me say, -1. And so there's a link that I can observe. So the radius was value of x0 to the power -1. And the power -1 is what I call logarithmic slope. Okay? Yeah, well. Oh? Yes, that would be bad because otherwise I would have another 60 slides. No, sorry. It's essentially related with the valuation of those coefficients. So you have to apply a change of variable and then transform 0 at infinity. So 0 becomes now a singularity after transformation. And you realize that this differential equation comes with an 1 over t square at the denominator, and the square is the valuation of the matrix of the connection. And that valuation in this case is the irregularity. Now, a spoiler about the sequel of this in this talk is that the radius of convergence contains actually the information about the Durand cohomology, the finite dimensionality of the Durand cohomology. Well, you might have the impression that the radii only depends not on x but on the value of x. This is not true in general. Yesterday I spent my entire day introducing an example, but they are so huge that I would have needed more time. So I decided to give you only the idea. So this is similar to the behavior that a radius may have. So it's kind of, you take a polynomial here, or more generally an analytic function, take the norm, do the inverse, and you take the minimum with certain constant. Well, why are we searching for the radii of convergence? Because they are invariants of your differential model. If you change base in the model, you have the same radii of convergence. Or if you have morphisms between a model and another, the radii are preserved, let me say, by this morphism. And then, as I said, they contain information about the cohomology. For instance, let me consider a more general case where f is general. Then there's a principle, let me say, it's not really, I have precise lemma about that, but I mean, it's better to say that if the norm is large, then for almost all x0, we have such an equality. So here, rho is just the value of x0, and the rho norm of this is the supremum of the value of fx or x of norm rho. In the cases that we will consider, this will be the rho Gauss norm. When f is small, when the values of f are small, actually the radius can change, the radii of the solutions move, and nobody knows in which way. They of course depend on f, because the equation itself depends on f, but in a more complicated way. I was able to obtain result in this direction for rank 1, but not in higher rank. So, and then I can tell you this equation has a finite dimensional cohomology if and only if, when the norm of x approaches the radius of your disk, okay, this is supposed to be a disk. So when I'm close to the boundary of the disk, then the radius behave in this controlled way. So it is moving, yes, but only with the norm of x0, with fixed number c and s. Okay, I call this property log affinity of the radius, because if you apply a logarithm to this expression, s becomes a constant in front of the variable, which is norm of x. Okay, we will see in a second. So if you want to compute those radii, you face the following problem: the fact that the exponential function is not converging enough. So you will soon come up with this other function which converge more. It's called Harting-Haas exponential. Surprisingly, there are denominator here, right? P squared. So what is inside the exponential grows up as the norm of t goes to 1. And so the exponential is not, so the composite of the exponential with this power series is not supposed to converge a lot, because the exponential converges strictly less than 1. But then when you do the compositum as formal power series, a lot of coefficients cancel, and what you have converge in the end with radius 1. This can be generalized using Witt vectors. So you can put coefficients in front of your terms, and those coefficients are Gauss components of Witt vectors. So this is a huge machinery. Also, this machinery of Witt vectors contain a lot of congruences, let me say, if you know what they are. And then I have another set of congruences coming from Lubin-Tate formal groups. So I need the formal group. So if I want to deal now with the exponential of a polynomial, I have to multiply in the reverse order everything by the torsion points of a Lubin-Tate group. Unfortunately, I have no time today to explain you this beautiful kind of results, because I'm speaking about something else. But so allow me to say that the first person working on this was Dwork, as usual, with this exponential. Then after him, Roba, Carellotto, Cristolchi, Nellato, Matsuda, and finally myself. I was able to obtain a closed formula for example, so for differential equation of order 1 defined whose matrix is a polynomial. You take this polynomial and you construct some other polynomials, f1, fn, which are explicitly given by your matrix of the connection and the derivatives of it. But there is no direct, so you have to solve a system, and there is no explicit solution of the system. Every time you have a new connection, you have to solve always the same system. But and then this is the formula for the radius. So it's the converse of a maximum of some norms. The inverse. Okay. So now you can observe from this formula that you might have in the affine line. So this is A1 analytic. Let me say you have some disks, and so it depends on where those functions are great, right? So you actually have a sort of, you want to avoid some disk. So the radio, it's complicated to explain without using Berkovich geometry, and that's why I'm using now in a second Berkovich geometry to describe capital N. In this, yes, just the number of the functions. It is really, so if f is a polynomial, is the degree. Yes. Okay, so let me now change topic and speak a little bit about, so give you an introduction to Berkovich language. So why do we want to work with analytic curve, and why don't we stay in algebraic geometry? So comfortable, right? But the answer is that there are not enough points. So the more we have points, the more we have geometrical information. And we will see in this talk, the entire geometrical information is hidden in the generic points. If you only have the information around the rational point, you don't have the information actually. So I'm providing you with a little analogy between algebraic geometry and Berkovich analytic geometry. So when you are working with algebraic geometry, the basic bricks are the K algebra, let me say. In Berkovich analytic geometry, you want a topology on those. So you want to have a norm actually, and you want them to be complete. So in algebraic geometry, points can be seen as arrows to points, to fields, right? To fields. So equivalence class of arrows. In this word, field is not only a field, it has an absolute value. So if you might have points to the same field, several points to the same field with different absolute value. So the datum of the absolute value gives you different points. Well, in algebraic geometry, when you have a morphism to a field, you actually check the kernel, which is a prime ideal, and the spectrum, the spec of A, is defined as the set of prime ideals, right? Here, there's something similar. What you do is, yes, you can consider the kernel, it is a prime ideal, but you also have to take care about the valuation in that field. So you pull back the valuation on your B. And this gives you multiplicative semi-norm on B, which contains the information of the prime ideal too, but it gives you more information. So the definition of Berkovich space is the following. So you consider it is the set of semi-norms which are real valued, bounded. This norm is the norm of B. They are multiplicative because they come from an absolute value in a field, and they are compatible with the absolute value that you have on K. Okay, so the similarity with algebraic geometry, we have a map like this. Yeah. E is a Banach algebra, so it has a norm, yes. Yes, yes. I will give you a couple of examples in a second. For example, closed disk, the supremum norm on a closed disk, or functions on a closed disk, for example. As in algebraic geometry, we have, you take a norm here, so a point of the multiplicative semi-norm, a point of your B, and you can evaluate. But you can imagine your element, the element of your algebra as functions on your defined space. So every B gives you a function of this type, and the topology that you put on M of B is the minimal one that makes continuous all of them. And since the minimal one needs to, so somehow you have to pull back the topology of R by all those maps. And this is why the shape of the Berkovich space is made by, you will see in a second, is kind of similar to a real topology. M of B was the set of, yeah, multiplicative semi-norm. M is for multiplicative semi-norm. So then you can be more abstract and then glue. So these are local pieces. Then you can glue them to define analytic spaces. You already know an example of analytic space, actually, because an open disk and functions on it are not bounded. So they do not form a Banach algebra, but the disk is union of closed subdisks. So the increasing union of subdisks. So the open disk is an analytic space, and it is covered by closed subdisks. Okay, why do we think that Berkovich spaces are good? Because, especially in p-adic, we have the problem that the space is totally disconnected, and Berkovich spaces are connected, archwise connected. They are Hausdorff, and the continuity is something that we can understand. And another very important point is that they have enough point, which means that in other geometries such as state geometry or Renault ones, Ridge geometry, Meredith, there are several languages that provide you with a space associated with those Banach algebras. But the other geometries do not have enough points. So if you want to define, for example, the structural sheaf of your variety, you have to introduce the notion of Grothendieck topology. And so if you want to say what a continuous real valued function is using Grothendieck topology, it is complicated. And on the other hand, there is another very important geometry, the Huber one. It has too many points. So it's difficult to be continuous for that geometry. So Berkovich seems to be a good deal. So come back with two examples. So E is a closed unit disk and D the opened unit disk. So functions on E are just power series with an going to 0, which means the power series converge. p-adic. So because converging in p-adic means the general term goes to 0. Thank you for the question. So I'm still p-adic, but I can be also trivially valued. So this is Banach, and the open disk is a Fréchet. To converge for such a power series on an open disk, it means that an rho to the n has to go to 0 for every rho less than 1. As I said, it's a union of closed subdisks. And then the question is, what are Berkovich points for those two spaces? Well, there's a little proposition that tells you that all possible Berkovich points are supremum norms on closed subdisk. So the idea is that you have your disk, you have a closed subdisk, and your ring is made by function over the big disk. You restrict those on the closed subdisk, and they are bounded there. And moreover, taking the supremum norm on a closed subdisk is multiplicative. So, yes, but I hide this, as I said at the beginning. Yeah, thank you. Yes, closed disk. It's fantastic, right? I tell you, it's easy. And then the same holds for the open disk. So yeah, it's an analytic space. So now here is the picture. So so if you give me a rational point here, and you increase, so you consider a closed disk containing that point, and you increase your radius, then every closed disk gives you 1 point in the Berkovich space. And in this way, when you increase your radius, you obtain a path in the Berkovich space, right? And then this gives you a picture which is similar to this. So the Berkovich disk is actually a tree. If you have questions, do not hesitate. And as you can see, it is hardwise connected. So now I wanted to point out that if you consider one segment homeomorphic to a real, so one segment here, the topology induced by the Berkovich space is that the one that you imagine. So it is homeomorphic to a real interval. Okay? But if you want to know what are the neighborhoods of the points, this is a more complicated story. You have to include almost all branches. And for those that you don't include, you want, however, to include a little bit of them. So this was an open disk, okay? But the closed disk is like this picture. Well, you already have something in mind that can describe the situation when you have ZP, for example. So the unit disk closed in QP is ZP, right? It's ZP, and you have residual classes. Right, here you have p-1 points, and here you have disks going into points. The situation for ZP is totally disconnected. You can express the disk ZP as finite union of open disks. But in Berkovich, so those are the classes I'm speaking about. But this is not a covering in Berkovich geometry, because there is one point that you're not covering in that way, which is the supremum norm on the whole closed disk. Okay? So when you want to define continuous functions over ZP, you face this problem that you have you express your space as a disjoint union of opens. Then on every opens you can put whatever constant you want. It would be continuous. But with Berkovich, if you want to be continuous, somehow all those constants that you put have to be the same, because they have to coincide on the red point, which is the boundary. So as you can observe, the space is still connected, and the point there is called the boundary. Okay? So now let me introduce you to annuli. So an annulus is the set of points satisfying such an inequality. And then what does it mean to converge on an annulus? What is a function on an annulus? Is a power series indexed on Z now. And then you want an, the coefficients, the rho to the n going to 0 for n going on the right and on the left, at infinity or minus infinity. Now, the same points as before are here. You have supremum norms on closed subdisks, but you also have other norms, rho Gauss points, which are given by supremum of the coefficients rho to the n. Okay, so this set of points is homeomorphic to the open interval Rs, and it is called the skeleton of your annulus. So my annulus has the red part, which is called the skeleton, and then other disks, disks centered at rational points, which are open disks of radius, the values of C. Okay, they are branched there on that skeleton in this way. This is really a topological way of thinking. Now, an operation that I'm going to do in a second. If I have an open... The cones are, yeah, it's a simplification for a 3. It's open disks. Sorry? Yes, so the disk, so disk is a tree. So all of this picture is for me yeah, just a scheme to say those are disks. So let me consider one open disk, and I consider a point there. What happens if I remove one point? Points are closed in this geometry. So what I obtain is an open annulus over there, plus this joint union of open disks. I have this open disk in the bottom, but I have similar disks which were probably branching at that missing point. Okay? So this is the picture. Because I tell you this because I have this nice theorem. So the distance between the right, so I have this disk, I remove one individual point. And then what remains is precisely one annulus, like that one, okay? And a union of disk, a disjoint union of open disks. Yes, I have this part over the point, over the. Thank you. So the distance between disk and annuli and general curve, it's not so far. Because we have this excellent theorem, so if I ask my curve to be quasi-smooth, let me consider it as a black box, a smooth curve. So the open disk is smooth, the closed disk is quasi-smooth because it has a bit of boundary. Then inside my curve, which is a graph, there is a locally finite subset formed by convenient non-rational points, such that if I remove those points one by one, what remains is a disjoint union of annuli and disks, open annuli and open disks. So S is called a triangulation. So the picture of my curve is that the blue points there are points that in S that I remove, and when I remove those, I remain with annuli and possibly some disks. No, most of the time is an infinite disjoint union. So the union of the skeletons of those annuli plus the points of S that I have removed is form a graph, a finite, locally finite this time, graph inside your curve, which is very important because it describes topologically the curve. The curve retracts on it by homotopy retraction. So everything concerning the homotopical invariance is in the red graph. And I call it the skeleton of S. Because what is a triangulation in classical sense? It's a set of points, such that when you exclude those, you remain with simple pieces somehow. The simple pieces in this context are disk and annuli. I agree with you, yes. So the name is this. So this is the picture for the projective line. Okay, this is the affine line. So you have to imagine it as a disk with infinite radius, right? So it's a tree like this. At infinity, you have one point missing, which is plus infinity. This is another curve. It's a Mumford curve. Of course, if I want a triangulation of it, I have to remove this point and this point. Here I have an annulus, and here I will probably have other two annuli. Okay, now, in order to show you that this can give you information also in a context that you know, I would like to. Oh, well, the tropicalization is something that lives in R to the power n. It's related. There's a theorem that no idea. But there's a theorem that says that the limit of the tropicalizations of your curve gives you topologically at least the Berkovich space. But you cannot recover the structural sheaf from the tropicalizations, nor the genus of the points. This is a notion that I will hide in the talk. So let me assume that the field is trivially valued. So what's a disk in this case? Well, it is the ring of functions is just the ring of power series, and the tree is not a tree, it's just one segment, like this. So the only possible norms that you have are given by this, and the row Gauss norms, okay? So you have these segments. This is very funny for me because when I was a student, some very important professor was explaining algebraic geometry to us and was quoting this ring as a trait in French. This means little segment. And I was really not seeing where the segment was. So, but in Berkovich geometry, you have a space, which is a little space, but it exists, where formal power series do exist, do live, do, let me say, converge. So notice that the only rational point is 0 in this disk because it's trivially valued. So when I say supremum norm on the disk, I mean supremum on possibly extension of K, which are possibly non-trivially valued. Okay, so what's the ring of functions over an annulus? It's the formal power series with T inverted, so the field of power series. And when you change your annulus, the ring is always the same, but what changes is the topology. Actually, the restriction is continuous, but not, it's inverse and bijective, but the inverse is not continuous. So the datum of the norms that you put on your ring tells you which kind of interval are you're looking. So it tells you the geometry of this object. So another example that I would like to tell you with trivially valued field again. So if I consider the scheme, the affine line as a scheme, I have rational points. Let me assume as usual that K is algebraically closed, etc. And I have a generic point. But Berkovich has a lot of more points. So as all those lines plus one line going toward infinity. And it has, in this sense, a lot of generic points. Okay, and then we have kind of topological structure around the generic points that you somehow have difficulty to see here with the language of schemes. So what's a neighborhood of the points? For 0 here, you consider one neighbor, it's an interval containing this point, and the ring of functions over it is just this for every such interval. If you consider a point in the middle there and a little segment, so the ring of functions will be this is an annulus, so this will be a formal power series. But if you want a neighborhood of this Gauss point, which is the generic point, then you need to consider all branches up to possibly finitely many of them. And in this picture, I excluded only one, but you also want to maintain in your neighborhood a little piece of it, little segment in it. You shouldn't exclude entirely one branch. And then the ring of function over it is this. Okay, it's the algebraic. It's nice algebra. So this kind of neighborhood is the situation for this x1 point is similar to what you have in a general curve over a non-trivially valued field. You have to include all the branches up to finitely many, and for those finitely many, at least a piece of them. So let me come back to the p-adic differential equation then. And then I'm also including the case of a trivially valued field. So why are them interesting? Maybe you know better than me why. So because we can do p-adic homologies, we can count points of variety, consider zeta functions. There are relations with G function, periods, algebraicity of solutions, p curvature, etc. I can do codifferences equation, and there's a strong link with p-adic representations, p-adic algebra, ramification theory, etc. So what's a differential equation then from now on? This will be locally free sheaf of finite rank over OX, though with a connection, which satisfies the Leibniz rule. So I will not work too much with such an object because I have a theorem that tells me that a curve, which is quasi-smooth, is either projective or quasi-Stein. And in this case, when it is quasi-Stein, my f is just a module over the ring of functions of my curve, and the connection is given by, you can pick up a basis if it is free. At least locally, it is given by a system, differential system of this type. Yes. Yeah, the points, when I say curve, I mean Berkovich curve. So I want a lot of points. I want all the Berkovich points, yes. It is the points of the curve, yes. Every Berkovich point is a multiplicative norm. No. The space itself is a curve. I mean, you understand what I mean? The disk is a curve, an open disk, for example. Okay. It's not a real curve, it's a curve in the meaning. And then what is the rank homology? You just have to take locally, at least, it's just the kernel of the connection and the co-kernel of the connection. Okay, I'm implicitly trivializing my object because I should write f tensor omega 1, but since it is a curve, the omega 1 is locally trivial and isomorphic to the sheaf. So this is the, so I just have H0 and H1. If you really want to do the general case, it's not far from this. You might have an H2, and you have to use the Haber homology, but I do not insist on this. So about the story of p-adic differential equation, the story has a date of birth, let me say, where Bernard work around the 60 proved the rationality of the zeta function for an algebraic variety of positive characteristic. And he used some special function that he proved to be related with differential equation later on. So he proved later on to be related. And then this is a key point in the history, because I think at that point people understood that p-adic numbers were concretely useful to prove theorems. Later on, we have huge works and with plenty of huge ideas by Dwork and Roba, but they were working over the affine line and with, let me say, local domains. This was enough because almost all phenomena show up on the affine line, more or less. And or over local domains such as the Roba ring. In 2000, we have an important progress made by Kristall and Mepkut. They proved, so they was working with differential equation over the Roba ring, and the aim for them was to prove finite dimensionality for the rigid cohomology of, which is a particular kind of de Rham cohomology. And the differential equations for them are supposed to have Frobenius, and the functions are supposed to be over-convergent. They don't deal with closed disks. They want only open disks somehow. And there is a strong link with p-adic representation. So 10 years after this, we started to attack differential equations in general, with no assumptions, no Frobenius, no overconvergence, nothing. Berkovich curve. And so the point of view is somehow orthogonal to that of rigid cohomology. We do not start from a problem in positive characteristic. We just want to have a Berkovich curve, a differential equation with no restrictions. And if you, so with this degree of generalities, the problem was almost unexplored up to 13, the problem of the de Rham cohomology. And there are no criteria to describe the finiteness of the cohomology. So there are some results due essentially to Dwork and Roba. Kristall and Mepkut, of course, treated an important case and developed several methods that are also useful for the other case. But they have a class of equation whose behavior is really, really kind. You don't see infinitely. So the presence of the Frobenius in the machine makes the radii of convergence to be almost constants everywhere. This is a good advantage. So let me speak about the radii of convergence. So first of all, I should define those, right? The point is that I would like to pick up a rational point, a disk, use Cauchy theorem, but if I consider a point of Berkovich, which is a seminorm, I can't do that, cannot do that. So the idea is that I have to extend the scalars of my field, and then this point becomes rational. And then it has also a neighborhood isomorphic to a disk. And then working on that disk, I can construct a basis of solutions and consider those radii of convergence. Okay, so the space of solution at a point is filtered by the radii of convergence. And this filtration depends in a way that I'm not going to describe from the choice of your triangulation, because the triangulation tells you how big it is, the disk where the points live. So I obtain from the filtration a set of radii. So in your mind, for every solution around my point, I associate a radius. And then I want precisely n radii. So now I want to consider a basis of solution which is adapted to this filtration. And if the dimension of f is n at x, then the space of solution is a vector space of dimension n. And I want to have the radii of a basis which is a basis of solutions which is adapted to the filtration. So two of those radii can be equal, For example, I may have a differential equation where solutions all have the same radius of convergence. In this case, all those radii will be equal, okay? So this definition is not very precise, but take it as it is. So I obtain in this way a function on my curve. And when I say curve, I mean you can imagine the disk, right? This tree. So for every point in the tree, I have a value, several values actually. I have n functions, okay? And what I call convergent polygon is precisely this ordered set of logarithms. Yes. Mm. Yes. Yeah, okay. Coming back in a second to what you know, I think, I hope. So let me do a step back to the trivially valued case. So now we have differential model over power series, right? An object that you know very well. In this case, the open annulus is 0, 1, and the triangulation is empty. So you can prove that if you give me any differential model over this power series, what happens if I move my rho, my Gauss norm? So the radius is given by a very simple formula, rho to the SI. So the information of the radius is all contained into this number S. And what are those numbers? This is precisely the formal neutral polygon, the one that you're able to define taking a cyclic base and the valuation on the coefficient of an operator associated to my model. And you know that you have this decomposition theorem according to the slopes of the formal neutral polygon, right? And you might see this as a decomposition according to the radii of convergence of the solutions. Okay, so let me consider the logarithm of the radius because I can see then my S going up. So as I said, the theorem tells you that those exponents S are the slopes of the formal neutral polygon. So in this picture gives you the picture of the radii of convergence of my differential model. And I might have, for example, 2 radii that are equal or even 3 that are equal, okay? And when they are separated, when they are distinct lines, then my differential model breaks. That's the idea. So I can interpret the classical decomposition result as a result. So the basic idea is that if I have 2 different solutions with different radii of convergence, it's because the model itself breaks. And then here is the decomposition result. So the differential models in my context are possibly not cyclic. And even when they are cyclic, the coefficients of an operator are not stable by base change. So their valuations move drastically. I cannot obtain any classical polygon from those coefficients. So the good substitute is consider the radii of convergence instead, but if I'm not in a trivially valued case, the space is not just a segment, it's a graph. And the radii function may move in a very strange way. In a moment, I will tell you that they move in a controlled way. And they are possibly not separated. They meet and they move. So the first theorem is that the radii of convergence move in a very controlled way. Okay, so they are continuous functions with respect to the Berkovich topology, and they are locally around every point constant in every direction. There are only finitely many directions out of every point on which they can do something different from being constant. Okay, so they are locally constant outside a finite graph. Yes, I agree with you, this is difficult to digest. I tried to do some picture. So this is my curve. The red part is the skeleton, and the blue part is a locally finite graph, which goes inside those disks. And the radii may move on the red and blue part. But then outside there, they are constant and continuous. So you can deduce the rest of the function from the behavior on this finite graph. Okay, so the decomposition theorem is that if for an index I, two radii are distinct at every point, then your differential model split. This kernel takes into account the radii of f, which are greater than this index, and the other takes into account the radii that are smaller. Okay, so this is precisely the decomposition over C of x by the slopes of the formal neutral polygon, the one by Malgrange. Rob obtained a similar decomposition, not for a curve, for one point actually, in a curve. So this is a differential field, and you can define radii for differential models over this field just as numbers. Space here is 1 point. And then I have other classical decomposition, including Kristol and Mepkutz. Okay, all those decompositions are local nature, and they are all in direct sum. But actually, we have an example which is explicit, where the sequence is non-split. And then we also provide criteria in order to be split. One of these is that it's compatible with duals, but the other is more interesting. It tells you that the position of those graphs with respect to the next one has to be like that. So as you see, those graphs, which are topological in nature, they tell you an algebraic information on the decomposition. It tells you that it is direct sum or not. So we can measure the size of those graphs. I don't give you any claim about that, but I can measure, and the measure is related to the indexes. So allow me now to come to this story about index. First of all, I don't want a general curve. I want a curve which is finite. So the Ram homology of the curve is finite. This is the definition. And I can characterize in topological terms those curves. Roughly speaking, so this is the trivial differential equation over the curve. So this tells you that the curve is obtained from a projective, excluding some finitely many disks, closed or open, or even finitely many points. So it tells you in particular that the genus is finite, and you have a finite skeleton, and several things are finite. So I have a bunch of notations here, which I skip. So I have to define the irregularity for my f. There is a Deligne formula holding for differential equations over complex numbers, complex curves. And then the index formula relates the dimensions of the cohomology with some topological numbers, some numbers, some local, around every singularity you have something called irregularity. at that point. Here, there's something similar at every, so the curve is a graph, and that graph may have, maybe a complicated graph, but in the end, it is an annulus, which is open here. So at infinity, you might have a curve, like the disk has one end which remains open. And you have to consider this function, which is the total height of your polygon. Remember, for every point you have radii, for every point you have a polygon, and the polygon moves on that curve. So when the point approaches the infinity somehow, the height of the polygon has a last slope. It doesn't have infinitely many changes of slopes. Okay, and then if it has this last slope, I have to count all of them, take the sum of those slopes, and then some other similar invariants at the point of the boundary. Well, now it's finished. It's finished. I'm sorry. Apologize. I have 4 minutes off. Okay, so this is the theorem. So I consider a differential equation, and I assume a technical assumption plus the fact that the radii are not maximal. So the round cohomology is finite dimensional if and only if the total height h of the polygon is affine when you approach the boundary, when you're at infinity. So if you have your open disk, when the norm of x0, you remember the example, approaches the end of the disk, the radii stay with the last slope. They do not break the slope again and again infinitely many times. And we have this index formula where you see appearing this number. That's all, more or less. There are three examples where this is automatically satisfied. It's when you have a meromorphic singularity, or when your differential equation is the restriction of another differential equation living on a larger domain. So that more or less all I wanted to say. Thank you very much. Sorry.